So we'll do some SEM now, because a lot of people ask questions about SEM. I added this last night to give you a little more flavor of what you can do and what you can get with SEMs. So this is a scanning electron microscope. Scanning electron microscopes comes in different forms. You have tabletop ones, you have the big ones, you have the field emission microscope, which one of this is. You have the one that is environmental SEM, where you don't have to dry the sample. You have the low vacuum, you have the high vacuum, you have all those different categories. So to choose what SEM you want to try is not that big of a deal in cement-based materials, because pretty much all SEMs can work for you. But if you have some water in your sample, environmental SEM is the best thing. If you want to have backscattered, then you have to have a very good surface coat. Even for secondary, you want to have a surface coat so that charging problems are avoided. Okay? Then there are issues with beam current, the voltage of the current, the spot size, the probe diameter, the resolution, accelerating voltage, all of that. Many of these SEMs go from accelerating voltage of 5 kilovolts to 30 or 40 kilovolts. Resolution is different. But if somebody has done this in the past, again, you don't have to reinvent the wheel. A lot of people would have done it. Your institution, somebody would have done it, or you can look at some papers and do it. So that's not that big of a deal. I don't want to recommend any one standard measurement for this, because it will be different for different conditions. Okay, so here is a secondary mode SEM of a certain sample. You can tell what these things are, right? Has to be fly ash. If you see something spherical in concrete and you know you've put in fly ash, there has to be fly ash. There is no other way. That can be something else. And then you can have a mass of all the other different things. And like I said, here's a scale bar. That's 10 microns. That's 20 microns. This is a system with powdered iron in it. So we were trying to create a more ductile composite. So it has some powdered iron, angular powdered particles of iron. So here is an area EDX. It's not a spot, it's an area EDX. So you define an area and you get the area EDX, and you see what you have. You have some iron, you have alumina, silica, calcium, iron, and then you can get weight percent and atom percent of what you have from EDX at that location. So weight percent of carbon, oxygen, alumina, silica, calcium, iron. Carbon is because this was stuck on a carbon tape. So you have some carbon from that. And then that's a spot EDX. You see how different the value is. This is basically on an iron particle, and you see everything is iron. A little bit of silica, maybe some dissolved silica is there on the top of it. Very little, but you see mostly all peaks are iron peaks. And if you look at it, there's a little bit of silica, very small, but again, maximum weight percent of iron. Right? Yes. Yeah, total ideally should be equal to 100, but I might have not added some of these very minor peaks of something else, so you would have missed it. You don't have to, no, you don't have to manipulate, no. So that's another thing. So a lot of people have this misconception, everything has to add up to 100. Theoretically, everything has to add up to 100. But there are so many things that you might not have figured out. There are so many things that you might not want to know. There might be some manganese there. Who cares if there is manganese? There might be... You can put in others. Yeah, you can put in others and make it 100. But again, I wouldn't recommend you to play around with what you get from because our concept and perception of what it is there is not as refined as a point where you get that value from an EDX. It's such a refined instrument. It can calculate to its atom percent, right? It can calculate to such fine values. It's better not to question it if everything else is correct, unless you have the real reason to make it 100. We can say there are a lot of other things that I don't know that will add up to 100, but hey, I'm worried about silica and alumina. Am I getting that? That's all what you're looking at. Okay. So this is an electron micro probe that we have. It's a newer hyper probe which can do backscatter electron imaging analysis, quantitative. It can do actually map analysis also. So you can do electron mapping or element mapping and see what is the dispersion of different elements in your microstructure rather than doing point EDXs. So So you have to, again, sample preparation is very similar. So that's a sample in an epoxy, polished ground nicely, vacuum saturated, polished nicely. So you look at the effective polish with a microscope to make sure that it's really nice with a lot of grits. Again, I just put this because somebody was asking about sample preparation yesterday. So again, some idea about how to prepare samples. Coarser to finer grade, 15 micron silicon carbide, 8 micron silicon carbide, 3 micron diamond suspension, 1 micron diamond suspension, 0.04 micron colloidal silica. By the time you've polished this, you can do your makeup on the sample. You can watch the sample and get your makeup done. It's be that smooth and that polished. 0.04 microns is the roughness effectively. So it takes a lot of time. It takes a lot of effort. We have a few systems where you can actually do 6 of these samples polishing at the same time. But still, it's a good amount of work for a student to get this ready. But if you don't get the sample right, you don't even know what you're getting, right? You might be getting a lot of irregularities, impurities. You might be interpreting them wrong. Also, think about it. When you're quantifying something, you are, and I'll talk about this when we do image analysis, maybe later in the day or tomorrow. When you're quantifying something, you want an extremely level surface because you're quantifying on 2D. Once you have slight aberrations on the surface, that becomes 3D, right? So you're doing 2D quantification, you want it to be really level, otherwise your quantifications will go wrong. Here are the samples after doing 8 micron silica. You can see some rough edges, 3 micron diamond suspension, some more rough places. By the time 0.4 micron colloidal silica, really nice and smooth surface. So here is a sample with which will be the densest particle in the system. You see that's not cement, that is an iron particle, and you see that's a particle of iron. You see why it's really bright, because iron is very dense, right? Density of iron. So, and then you have some pores. You have a fly ash particle here. You have another fly ash particle here. If you see here, you have a bunch of pores here. You have a few more iron particles, needle-like iron particles here. Another fly ash particle. So you can look at all of that. And then I'll show you here. This is an iron mapping. Electron microprobe mapping of iron to tell you exactly where the iron are. So all the yellow spots are where the iron is in the microstructure. So you don't see it in the holes, but what it tells you is if you put in just iron particle, and we have put in some mild acids also in the system to make the iron more bonding to the surfaces, you can see that iron has diffused from these particles all through the microstructure. So I want to know what is the distribution of iron. I want to know if the particle that I'm putting in is spreading all around. Right? For example, if you put in fly ash alone, and then if you want to know if silica in geopolymers, for example, if silica from fly ash is spreading around and going all over, you can look at this and see if the silica is spread through or if silica is localized in one place. That also helps you find out the degree of reaction, right? How much of reaction has happened. This is a mapping of silicon. You see here the main iron particles devoid of silicon. Everywhere else, look at the fly ash particle, right? Rich in silica. And if you do an aluminum mapping, you see here devoid of alumina, but you will see some alumina in these fly ash particles here. Alumina here. You can do calcium mapping. This particle has a lot of calcium. That's pretty much the only place that you see a lot of calcium. So that could be a fly ash particle with some calcium impurities. Okay, so basically you have some, even in class of fly ash, you have small amounts of calcium, right? That could be one of that. Carbon mapping, we have carbonated this sample. So this sample was subjected to CO2. So some of these reaction products are carbonated. So you can see carbon all over. All of these can be quantified. So if you do image analysis on these, you can quantify how much of these things are, which we'll talk about later. And if you want to do a quantitative analysis, again, there's a point EDX here. You can see that point. You see iron, some silica, iron, some iron. Again, you can find out what the total is. Atom percent is 100% matched. Mass percent is not matched 100%. Anybody wants to suggest the reason for that? Atom percent is matched, but mass percent not matched. But voids have no mass. Which one would be correct? Which one would be more correct? No, this is an atom probe. What this is determining are the atoms. Okay, so it's actually determining atoms. So it's finding out all of these based on the atomic concentrations. The probe is an atom probe. And mass is derived from the atomic percentage by telling you that, okay, carbon has an atomic mass of 12. But even if you look at the periodic table, it's not exactly 12, it's 12.006 or something, right? So when I calculated that, and this is our calculation, we just simplified it. That's because we missed all those decimals, we just simplified it. Okay, so atom percent is correct, mass percent is derived from atom percent by using the atomic number, and the atomic numbers are not always whole numbers. So we missed that part. Yeah, you can do that. Yeah. Doesn't matter. Doesn't matter. That's your software. Whatever software you're using, you can get it whatever you want. So here is again, here is a place where we have made sure that, see this decimals in the mass graphs here, we have made sure that we matched it to 100 for anybody who gets upset if it's not 100 on both sides. Okay, I am okay, but if you're not very happy with not seeing hundreds on both sides, that's another one for it. Okay, so let's get into image analysis. This is very interesting. Okay, and I'll give you some practical tools for you to play around in your free time. Give it to your students. I'll show you some nice tools also. Okay, so a lot of illusions in image analysis. Again, like I say, pitfalls. Let's do the pitfalls first, and then I'll show you the theory. If you look at an image, and I'll show you a lot of images. If you look at an image, beauty lies in the eyes of the beholder, right? Any image, you can interpret it based on your judgment. Some people will see some wonderful scenery if I give them a picture of a forest. So we take this common example, Grand Canyon, right? I live in Phoenix. Grand Canyon is only 4 hours away. So a lot of friends and relatives come, and Grand Canyon is like a pilgrimage to temple. I've gone to Grand Canyon so many times that it becomes very boring now. You take them. For some people, love it. This is this majestic thing that the Colorado River has shaped over millions of years. You have this canyon. You've seen pictures of Grand Canyon, right? No? If not, I'll show you. I have some pictures. Maybe tomorrow I'll show you. So this majestic canyon, miles and miles of this canyon, this beautiful ridges, ups and downs that nature has created in between some elevated portions. It's all the play of water. The river has carved the limestone over millions of years, right? This is beautiful. Some people say, oh man, wonderful, this is so beautiful. Some people say, what is this, just a hole in the ground, right? So again, beauty lies there. Some people will think Grand Canyon's great, it's one of the 7 wonders in the world. Some people will say, nonsense, I traveled all this way to see the hole in the ground. So depends on what you think of, and images are also like that. So perceptions are different, and that's why we have to focus on what we are looking for. Okay, line distortion illusion. I'll skip this. You've seen such pictures, right? The illusion pictures, the mystic wheel. It's called the mystic wheel. You might see the illusion shimmer slightly. Are you guys seeing it? You might see the illusion shimmer slightly. This is because the lenses of your eyeballs are slightly out of round. They are not spherical. Watch. If you have a convex mirror that is a zooming mirror, keep your face close to the mirror and watch your eyeball. You can actually see that your eyeball is not completely spherical. Okay, or if you can take an image of that and draw a real cycle around it, and you will see the edges of the eyeballs here. It's like an ellipsoid. That's why you're seeing it. Parts of the illusion move in and out of the focus. As your eye scans the image, looking closer, you will get a 3D impression. You can see that, right? You can feel that this is deeper and this is on the surface, right? So, but do I have a real 3D image? No. So that's another thing. That's what you're getting in a secondary SCM. Don't you see that your calcium hydroxide is higher, the cement paste is lower? You see that, right? But that's because you have secondary image and you don't really have You're seeing in 2D still, but our eyes can perceive 3D even in 2D. Now follow the ring of the curves nearest the outer edge around the wheel, and you will see the geometry grow from hump to hollow, which is an impossible trick in 3 dimensions. Look at this, okay? You can carefully look at this. You will see the outer dimensions. You will see that happening, which you cannot do that in 3D. What I want to show is what you see in 2D is a fallacy. What you see in 2D is fake. You have to make sense out of the fake from 2D. Anytime you look at an SEM, tell your mind, I'm looking at a fake picture, I need to create the right impression out of it. Because if you take a 2D of a 3D structure, and I'll show you some mathematical tricks to do that as we go through, what you're effectively seeing is a 2D structure, not 3D. Now here is another illusion. See here, and I'll show you the next one where this is. So you can see a fish here, a boat with something here. You can see that? Another fish attacks him, and then what do you see here? I just inverted the picture. Now you see a duck with something on its beak. Same picture. I just inverted the previous picture. Here it's all trees and river and a fish and this. I just inverted it. See what you have? This is exactly what you have when you play with images. And that is why you can interpret it whichever way you want. You can think what you've done is right. But that's why you need to really understand what you're looking for. Anybody can interpret. So when somebody comes and says, and that's why we need to know calcium hydroxide is crystalline and it has a certain shape. Ettringite has a certain shape. CSH is amorphous. Fly ash is spherical. Fly ash can have spheres inside. Those are the facts. You have to merge those facts with what you see in those pictures to create the interpretation of, again, why do we need an SEM picture? Okay, I probably missed asking that question. Why do we need an SEM picture? Do you need it? Why do we need it? Do you need an SEM picture to build the road that goes this way or this building? Do you need an SEM picture? Why do we need it and when do we need it? Why do we need it? If you don't need it, I'll skip this entire topic. We can go to the next. If you think that you don't need it. Because there's no point in talking about something that nobody needs, right? Do we need it? For what? When do you need an SEM picture? To find out the morphology. When do you want to find out the morphology? Why do you want to find out the morphology? Huh? What is that? You want to change the properties, you want to understand what's in the microstructure. Again, I gave you an example. You can tell me back the examples that I gave you. You can ask me, when I ask you why do you want to see a microstructure, you can just ask me why does a doctor want to see an X-ray? Right? You can ask me back the same thing. Why does a doctor want a CT scan? Just for fun? No, to find out what the problem is, right? Somebody comes and says, my concrete is cracking, my concrete is not reactive, my concrete is not setting. You want to find out why it is. Most of the time you do look at SEMs to understand what has formed so that you can solve a problem. If there is no problem in a bridge or a road that you've created, you don't waste time doing an SEM. And then when you develop a new material in the lab, when you design a new material, when you do geopolymers, recycle aggregate concretes, whatever you're doing, when you develop a new thing, you want to know why it is giving you the properties you are getting, right? So that's the reason why you look at it. You don't do it just because, I want to check if calcium hydroxide is actually tetrahedral crystals. Nobody does SEM for that. It's too expensive to do. So when school kids come to our labs, I show them all of those. So some of these very innocent small kids, right, 5th grade, 6th grade kids, Professor, can I give me my ring? Can you look at this and show me what's inside my ring? I said, it's too expensive. You would have bought a $1 ring from the corner store. It's too expensive for me to show you what's inside the ring. Ask your dad. Right? If it's a real gold ring, they'll know it. Okay, so again, you see those rings rotating? Are they really rotating? No, it's all illusion. So I just want to give you a feel for what you will have when you look at an image so that you know what you're looking at. Okay, now to the boring part. Those are all nice pictures and you can have fun. But the boring part here is a lot of terminologies. Resolution, pixels per mm, pixels per inch, all of you know that, right? Even if you're taking, now all of you know it, right? you ask immediately, what's the resolution of the camera in your smartphone, right? You do that. Right? So I want a camera, 8 megapixel camera with whatever resolution that you want. So you know what that is. So an image with a resolution of 100 pixels per inch, I do everything in inch because in the US we are still so retrograde, we still do inches and feet. So if you have 100 pixels wide by 100 pixels high, that's a 10,000 pixels in a square inch. The higher the resolution, more pixels in image. You know, if you buy a more expensive HD TV, what you're getting, right? More pixels per inch. Same idea. This is commonplace now. So you know what that is.